Welcome to the Explainer. Today we're jumping into one of the most fundamental techniques in all of chemistry. Think of it like being a chemical detective, where our job is to unmask the hidden identity of an unknown solution.
So, let's start with a classic chemistry problem. Picture this. You've got a flask, and inside, a totally clear liquid. Is it a strong acid or a weak one? Is it super concentrated or really dilute? I mean, how on earth do you figure out what's inside when you can't just, look at it?
Well, the answer is this really powerful, kind of elegant technique called acid-base titration. It's our #1 tool for this kind of detective work. The big idea is simple. We use a solution we know everything about to figure out the secrets of the one we don't.
So here's our game plan for today. First, we're going to nail down the big idea. Then we'll look at the classic strong acid-base titration. After that, we'll see how everything changes when weak acids get involved, tackle acids that have multiple protons to give, and finally, we'll wrap up with the practical tools you actually use in the lab.
Okay, so first up, the big idea. The entire process, the whole thing, really hinges on tracking just one key variable as we mix our known solution with our unknown one, and that variable is the pH.
You see, as we carefully, drop by drop, add our known solution, that's called the titrant, we're constantly measuring the pH. And when we plot those measurements on a graph, we create what's called a titration curve. And this graph, it's not just a bunch of dots. It's the whole story of the reaction, laid out visually, and it holds all the clues we need to crack the case.
All right, let's kick things off with the most straightforward case you can get. Titrating a strong acid, like hydrochloric acid, with a strong base, like sodium hydroxide. This is the textbook example.
And when you do this, you get this classic, you can't miss it, S-shaped curve. Every single time. The shape of this curve tells a very specific, very predictable story about how that acid and base are perfectly neutralizing each other.
So let's break down what this S-curve is actually telling us. First, you start way down here, at a super low pH, right? Because it's a strong acid. Then, as you add the base, the pH starts to creep up. And then, whoosh! It shoots straight up in this incredibly steep climb. Right in the middle of that crazy climb is the equivalence point. That's the sweet spot, where you've added just enough base to neutralize every last bit of acid. For a strong acid and a strong base, that point is always at a perfectly neutral pH of 7. Then, the curve flattens out again way up in the basic region.
Okay, so that was strong on strong. But now things get really interesting. What happens when our unknown is a weak acid? Something like the acetic acid you find in vinegar? Well, the story that the curve tells is totally different.
And you can see the difference clear as day. Let's break down the 3 big giveaways. First off, notice the starting pH. It's higher, not quite as acidic. Second, look at that flat, shallow section in the middle. That's called a buffer region, where the pH just refuses to change very much. And third, the equivalence point isn't at 7 anymore, it's shifted up into the basic range. Why? Well, because when you neutralize a weak acid, you create its conjugate base, and that base makes the final solution just a little bit basic.
Now, see that flat part, that buffer region? There's a secret hidden in there, a really important spot called the midpoint. As the name suggests, it's the exact point where we're halfway to the equivalence point. We've neutralized precisely half of the weak acid. And this is where the magic happens. This is the superpower of the midpoint. At that exact spot, the pH you measure is equal to the pKa of that weak acid. And the pKa, well, that's like a unique chemical fingerprint for an acid. It tells you exactly how strong it is. So by finding this midpoint, we're not just finding the concentration anymore, we can actually identify the unknown acid.
Okay, so we've done strong acids, we've done weak acids, but what if an acid can give up more than one proton? We call these polyprotic acids, and their curves are just a fantastic buildup of everything we've just learned. Take something like phosphoric acid, H3PO4. It's got 3 acidic protons it can give away, but it doesn't just dump them all at once. Nope, it loses them one by one in stages. First, the most acidic proton goes, then the next one, and then finally the last least acidic one. And because it happens in stages, the curve shows it perfectly. You get this amazing stair-step pattern. Each one of those steps is like its own little mini titration for one specific proton. It has its own equivalence point, and, you guessed it, its own midpoint. And at each midpoint, the pH reveals the pKa for that specific proton. It's incredible. All right, so the theory is awesome, right? These curves tell us so much, but let's get real. How does this actually work in the lab? Let's talk about the practical tools of the trade.
I mean, you could hook up a fancy pH meter and plot out the whole curve every time, but a lot of the time you just need a quick and easy visual cue to know, okay, stop, you're there, you've hit the equivalence point.
And that's where acid-base indicators come in. They're basically just special dyes that change color at a very specific pH. The whole trick is to pick an indicator that changes color right around the pH of your equivalence point. So for that strong acid-base titration where the equivalence point is at 7, bromocrestal blue is perfect. But for that weak acid titration where the equivalence point is, say, around 9, you'd want to choose something like phenolphthalein, which turns that beautiful pink right in that range.
Okay, final tool in our toolkit, the math. And look, pH calculations mean logarithms, which can be a pain, right? Especially if you're in a test and you can't use a calculator. But there's a fantastic shortcut.
Check out this amazing approximation. It's almost like a magic trick. To find the negative log of a number in scientific notation, like m times 10 to the minus n, all you got to do is take the exponent, n, and subtract 0.m.
Let's do a quick example so you can see how easy this is. Let's say you need the pH for concentration of 3 times 10 to the minus 5 molar. Here, n is 5 and m is 3, so the pH is going to be about 5 minus 0.3, which is 4.7. See? Super fast, and it's pretty darn close to the real answer.
And that's the whole story. Whether it's the simple, elegant S-curve of a strong acid or that complex, beautiful staircase of a polyprotic one, these titration curves are just incredibly powerful tools. They tell a complete story, letting us figure out not just how much stuff is in our flask, but very often exactly what that stuff is.
And believe me, this isn't just some abstract thing we do in a lab. This kind of precision is absolutely critical in everything from making medicines to ensuring our food is safe to eat. It really makes you wonder, right? What other invisible, precise chemical measurements are going on all around us, shaping our world in ways we don't even see?